So it's a pleasure to have Alexander Braverman talking about geometric Langlands and quantum supergroups.
Well, yes, I wrote here a slightly different title, but it's very, I wrote local quantum geometric Langlands and Lie superalgebras. Okay, maybe let me add also. And supergroups. Well, okay. I'm going to have a slightly, well, first of all, thank you very much for the invitation. And I think as far as I understand, this is the last talk of the whole conference. So I think we should all thank the organizers because, I mean, all these online events are usually especially difficult to organize. So my plan is a little bit maybe ambitious, but I'll try. I mean, I'll try to fit it into 50 minutes. I want to basically, my main goal in the very end will be to report on some conjectures originally made by David de Gaillota and about my attempts with some group of co-authors who are written here, Finkelberg, Kravkin, Ginsburg, and Zhitao Yang, to try to prove various special cases of those conjectures. I mean, to put those conjectures into some framework, I need to really introduce the formalism of local quantum geometric Langlands, which is something that I'm going to try now to do. So I'm going to talk about some, well, I'm going to give some introduction to the subject. Then, well, this will be some kind of quantum Langlands duality, so it will be duality between some object and some other objects, and then I'll give some examples of this. And actually some examples which were known before these Gaillota conjectures, and then Gaillota conjectures. I would like to formulate them as also examples of as a kind of source of examples of quantum Langlands duality. Where at least one side will be coming from Lie superalgebras or quantum supergroups. Okay, so that's kind of the idea of what I would like to try to do. Okay, so now, okay, so local quantum Langlands. Now, since this is strings math conference, let me first put it in some kind of sort of physics perspective, although I won't be really using that, but for motivation purposes, let me recall the following things. So first of all, I'm going to need to start with some group G, which is for now, let's say, some simple, semi-simple algebraic group, or even reductive algebraic group, because I mean, for me, one of the main examples will be the group GLN, reductive algebraic group. And well, to that, well, if you speak in a physics language, then one can study, well, the corresponding n=4 supersymmetric n Mills, and then Witten and Kapustin and Witten associated to this. A family of maybe partially defined, so it's not clear how well they're defined, partially defined topological quantum field theories, or actually better to say extended topological quantum field theories in dimension 4. So I'll say in a moment what this family is parameterized by, but just to tell you sort of the structure, what does it mean that, I mean, suppose that we in the ideal world, we have a kind of really well-defined 4-dimensional topological quantum field theory, then it's supposed to assign, say, numbers to 4 manifolds, so to say closed 4 manifolds, closed 4 manifolds associated numbers. then to well, if we have three manifolds, we're supposed to get a vector space. Let's say everything over complex numbers, so everything over C. Then if I have a two manifold, so the Riemann surface closed, then we're supposed to get a category. And then we also can have a one manifold, and one manifold, and essentially, well, up to taking disjoint unions, we have only one closed one manifold, which is a circle. That's one. To that, we're supposed to associate a two category. And so two categories typically something that, typical way to construct a two categories to consider categories, you consider the sort of two category of all categories endowed with some additional structure. So this is what we're going to see, and all this should somehow depend on the group G. And it should depend on group G, and actually one more parameter, which is usually thought of as a number, but I would prefer to think about it not as a number, but as something else. So, so kind of, I said that there's a family. So family is parameterized by invariant bilinear forms. Usually I'm denoted by the letter kappa on the Lie algebra of my group. So typically, I mean, like many cases, this Lie algebra is going to be simple Lie algebra, and then there's only one such form up to scalar, and you can normalize it in the same way, and then you can think about this form, this bilinear form, as a number. Also, well, what I'm saying now is actually only part of the truth. So you can actually extend this slightly. So you can actually make this number infinity. So so if G is simple, then in fact the correct space of parameters is P1 parameters. So if we is, let's see, CP1. So if we exclude infinity, then we just get a set of complex numbers, and that's essentially what I said before. But actually, there's more to that. Namely, you can also have this sort of infinite parameter, and which is definitely, from a certain point of view, one of the most interesting ones. But actually, for today's purposes, I'm going to ignore that. So for today, I'm only going to consider these parameters which have to do with bilinear forms. And in fact, I will even at some point assume that these bilinear forms are non-degenerate. So let's really think about this as being associated to this bilinear form, which again is for a simple Lie algebra. This is just one parameter. For other Lie algebras, it can be many parameters. And the thing I'm interested in is actually for local quantum Langlands is about this row. In principle, it should also associate a free category to a point, but this is something I'm not going to discuss today. So today I'm going to only discuss this row, this two category, which we now supposed to associate to we're now supposed to associate a two category to our group G, or maybe to Lie algebra G, and to this invariant form K. Okay, so what is the two category? To G and kappa? Well, the answer, well, I can have different frameworks you can talk about this, but sort of one possible answer, at least this is one way to think about the answer, is the following. So it's, we consider, so it's, okay, let me give you the answer sort of, well, as a slogan, and then I'll try to explain the terms. So answer we should consider two categories of categories C endowed, as I said, so we want to consider a category of categories endowed with some additional action, with some additional structure, sorry, endowed with an action of the formal loop group G round braces TT, here's some formal parameter, on level kappa. So let me spend a few minutes just making some remark about this. So first of all, one thing I'm going to hide under the rug is that when I say category, so actually, if you want to be really careful, then category should be not an honest category, it should be some kind of DG category and so on. So I'm actually going, so there's some kind of, so I mean, so it's not just a category, it's some kind of nice DG category, but this is something I'm going to totally ignore. And so what exactly do I mean by a category? This is, it can be said in this framework, but I don't want in this talk to deal with this. More importantly is that suppose we have some algebraic group, I mean, well, maybe some, this formal loop group, maybe I'll also sometimes denote it by LG. This formal loop group is, it's not really an algebraic group because it's infinite dimensional, but it's what's called a group in scheme. So somehow it's almost as good as an algebraic group. So there's a notion of that acting on a category, and now what I want to say is that this kappa, of course, defines a central extension of its Lie algebra of the Lie algebra of formal Lorentz series. This is a standard construction. So let me denote it by G kappa. So this is G hat kappa. So this is G T. Here C. So this is some central extension like this. So it depends on the choice of kappa. And so the claim is whenever we have an algebraic group and a central extension of its Lie algebra, you can talk about categories endowed with the action of this algebraic group on the level, prescribed by the central extension. So unfortunately, it will be slightly technical. I mean, it's not difficult to define it, but instead of giving a definition, let me give you a couple of examples. So examples. So, well, let me assume first that kappa is 0. So somehow let's forget about central extension for a moment. First kappa equal to 0. Then there are basically two sources of examples. And actually, let me do it in slightly different format. So let, as I said, let A be some algebraic group, and later on A will take A to be LG, and it's curly A is its Lie algebra. Then I want to give you an example of an action of a category with this action. So one example is example 1 is that if we take the category C to be the category of A modules, representations of the Lie algebra, then the group A acts here by adjoint action. And actually, here I actually can immediately introduce also the case when we do have kappa. So if we have this, if we have a central extension, if we have some, let's say A tilde central extension of A, then I'm by central extension, I mean central extension by complex numbers, then we can consider the category, another, let's say category C tilde. This is A tilde modules, where C acts in the standard way. So just element 1 and C acts by 1. And then this thing still has an action of the same group A by the same adjoint action. But if you make all the definitions carefully, this will be an example of an action of this algebraic group on level prescribed by the central extension. So A acts on sort of level. So you should think about the level as really the central extension of the corresponding the algebra on level given by A tilde. So that's one source of examples. The other source of examples is that, let me first still do it without the central extension, and I'll do it with the central extension. Let's suppose that we have X is some algebraic variety with an action of A. Then we can take C to be the category of D modules on X. And in fact, secretly, when I'm talking about, say, something like D modules, I always mean the derived category. And then the group AX here. So if it's take something like quasi-coherent sheaves on X, then the definition of this action is such that on the category of quasi-coherent sheaves, we don't. We do not have the action, or well, at least our notion of action is such that it's sort of adjusted to D modules rather than to quasi-coherent sheaves. With the central extension, we can let me actually assume that the central extension is well, okay, so I'll say that later what happens with the central extension. So okay, so for now, so let me say you can extend it to central extension. Then we need to consider some notion of twisted demodel. Twisted. So that's maybe a slightly abstract notion, but the claim is that somehow if you try to develop this Kapustin-Witten story, let me go a little bit back. If you try to develop this Kapustin-Witten story, then the two category you're supposed to associate to a circle is really this two category of categories endowed with an action of the loop group of level kappa. So let me say that so in particular, so let's denote this kind of by Langlands kappa. Let this be well, Langlands will sorry, I mean I also need to introduce G in kappa. This is this two category of category C with G of T action of level kappa. And so one example of this thing is that if we take our G hat kappa modules, so by this we mean, again, this is a representation of the central extension on which the center acts in the standard way. This is just one example of an object of this two category, but there are many more. And so now one other thing, of course, when we have the Langlands duality is well, we have the duality, and so in the Kapustin-Witten framework, Kapustin-Witten they study what S duality does to this story. S duality And this S duality, what it does is it changes our topological quantum field theory in the following way. First of all, we should replace the group G by, so G gets replaced by G check, which is Langlands dual group. But again, for today, all groups will eventually be products of GLNs. And so in that case, the dual group will be the same product of GLNs, but in general, you should have to replace it by the Langlands dual. What also happens with kappa is the following. So, well, first of all, it's convenient to well, okay, so let me say it like this. So I'll give you the answer for kappa non-degenerate. So assume that kappa is non-degenerate. That's actually case which is so. I mean, that's exactly what quantum case will be about. Or at least when. Well, okay. So I want to assume that kappa is non-degenerate, and now what I want to do is I want to say that this two category for G and kappa is actually equivalent to the same kind of two category, where I replace where I replace G by G check, and also I replace kappa by something else, so if you want to be careful, then I also want to introduce the critical level, kappa critical, and critical means that this is minus 1/2 of the Killing form. That's actually the canonical definition of critical level. And then the kind of what Kapustin-Witten, I would say Kapustin-Witten, maybe Gatesbury, what they will tell you at this point is that you should have a canonical equivalence between this Langlands for, well, let me write kappa plus kappa critical. Here I want to write also Langlands for G check. And here, well, it turns out that the correct thing to write is minus kappa check minus kappa check critical, where kappa check critical is just the critical level for the dual group, and kappa check is the following guy. There's a canon. If we have our Lie algebra G, then inside we can choose a Cartan subalgebra. And our form is uniquely determined by what it does to the Cartan subalgebra. Now, if I have the Langlands dual algebra, well, that's some kind of Langlands dual algebra, but it has the property, well, it also has a Cartan subalgebra. And so the main kind of property here is that H and H check are canonically dual to each other. Dual as, as vector spaces, or as commutative Lie algebras are dual to each other. So the Lie algebras G and G check themselves are not dual vector spaces, but H and H check are, and so our invariant form is the same as a form on the Cartan subalgebra, which is invariant under the Weil group. So therefore, we can think about our kappa as just a form on the Cartan, and if it's non-degenerate, then any non-degenerate bilinear form in the vector space gives you canonically non-degenerate bilinear form in the dual vector space. So that's so we can use this to build kappa check from kappa. So that's that's kind of the story. Again, sort of this numerology with critical level and so on, it's not very important. So the kind of the thing which is maybe more important is that if, for instance, you assume that kappa is 0, then of course kappa check is not defined, because it's only defined. So I mean, if you have a form on the if you have bilinear form on the on some vector space which is degenerate, then it doesn't define a bilinear form in a dual space. And this actually has to do with what I said before. So let me go a little bit back. So so I said that the correct space of parameters here was actually CP1. And this is and so the reason why you need to, well, I mean, in the case when G is simple, when you have only one-dimensional space parameters, then so the idea is that you this duality will then exchange in the correct if you normalize things correctly, this duality will exchange 0 and infinity. That's kind of what you need infinity for. But if you don't allow 0, or in general if you don't allow non-degenerate forms, then you don't need infinity either, and then you get just this thing. And so this thing, you can call it local quantum geometric Langlands conjecture. Now, this is kind of very abstract, but I want to emphasize that sometimes it actually gives you certain equivalences of categories, and this is where I'm heading. So so it means that this thing means that somehow given given C category with G of T action of level kappa, well, of level, or more precisely, this kind of, I need this critical shift. So let me ignore the levels for the moment. So we should be able to construct this to associate the C check, which is another category, with G check of T action. For example, we can take this affine Lie algebra G hat, give it central extension given by kappa, and we can ask, we can put it as C, and we can ask what will be C check. And I'm actually going to give you the answer in a few minutes. But before that, let me say that, I mean, this is just, I mean, so far we didn't even say anything about this. We just said that we have a category with some action of some group. We should be able to construct a category, a different category with an action of a different group, and also with some levels. So now let me give you some kind of at least one property this thing should satisfy, which will be pretty weak, but at least it will be, well, it will be sufficient for the purposes of today's talk. So properties of this, that so C should not be, by no means it should not be equivalent to C check. But it turns out that the following should be true. So if we consider this, let me actually introduce the following notation. Let me introduce the field K, which is the field of Laurent power series, and inside we have the ring O, which is the ring of Taylor series. And so our loop group is just the group G of K, and inside G of K we then have the group G of O, which is sort of like, I mean, if instead of C we were working with a finite field, that would be a maximal compact subgroup in G of K. So this is something like maximal compact subgroup. In fact, it's essentially maximal group subscheme, not group sub-in scheme, but group subscheme. But it's kind of much better behaved object. Now, if we're given a category category C. Again, by category, I mean essentially I mean some kind of DG category and so on. But if I have some kind of sufficiently nice category C with G of K action, you can take equivariant objects with respect to various subgroups. For example, with respect to G of O. You can take, I denoted by C G of O. This is the category of G of O equivariant objects. I will say I will give you some example of this in a minute, and then some people will recognize some familiar objects here. Category of G of O equivariant objects. And then the property should be, then, so everything is arranged in such a way that if C is dual to some C check, then C G of O should be equivalent to C check G of O, G check of O. That's kind of an important property. So I'm starting running out of time, so I'll have to switch to the super algebra stuff maybe in 5 minutes. So but before I do this, I need to. So actually, I have a question. When exactly did I start, and when exactly did I have to stop? Hello,
Henrique?
I mean, I think
I
think
you started like about 10 minutes. I didn't check, but I think it was about 10 minutes after the hour.
Okay, so then I should stop. Then I'm supposed to stop at like exact hour, right? Okay. Okay. So now example I want to consider is that C is equal to this G kappa check modules. Then CG of O, this is what's called the Kazhdan-Lustig category of level kappa. And this consists of G check kappa modules. Again, when I write G check kappa modules, I mean that it's modules over the corresponding central extended Lie algebra where the center acts in the standard way, which are G of O integrable. So it's important to say here that one thing I should have said is that in order for this to make sense, we have to. It's important to notice that this central extension, our central extension G check kappa splits over, more or less canonically, over G of O. So therefore, if I have any representation of this centrally extended Lie algebra, then it's actually, it gives us also, we can restrict it to just G of O, and then we require that is integrable, or which is in fact, if G is a simple Lie algebra, that's a property. If G is, for example, if it's something general reductive, it's actually structural property, but doesn't matter. So this is called the Kazhdan-Lustig category, and now maybe jumping a little ahead, let me say that somehow what we indeed assume that G is so if for generic kappa, for in fact, you have to exclude some particular list of kappas. Kazhdan and Lustig constructed an equivalence between this. I should let me actually call it. Yes, maybe just leave it C. So Kazhdan-Lustig constructed an equivalence between Kazhdan-Lustig kappa of G and the corresponding quantum group. Well, I mean, you have to ask. You can ask what is Q here. So Q is this is the category of finite dimensional representations, and Q is determined by kappa. So if you assume that the algebra G is simple, if you normalize things correctly, then if you think about kappa as a number, then the formula is something like Q is equal to exponential of 2 pi I over kappa, something like this. But this is, I mean, you have to interpret this correctly. So therefore, this category of GeO4 equivalent objects is a very familiar guy in this case. Now you can ask, what is C check? And this is a very basic question for local Langlands, and there's an answer to that, the answer is the following. Okay, so the answer is that you should consider the category. Well, okay, so here's, well, okay, let me give you the answer, but I'll have to again explain the terms. So the answer is that C check in this case is the category of, well, kappa check or minus kappa check twisted D modules on G of K mod. Well, let me write it and then I'll explain the notation. So U inside G is a maximal nilpotent subgroup. And kappa from U to the additive group, or in fact, also we can then write it from U of K. The additive group is a non-degenerate character, so the generic character.
So can I ask you a question?
Yes, sure.
I think it's related to this. It's from the previous slide actually. So you wrote the general statement that you had an equivalence of two categories.
Well, conjecture.
Yes. Yeah. So if you have that and you look at the category of equivalences, then that thing should have an action of G and G check, right? At the same time.
Well, yes. I mean, you're right that in principle. I mean, what do you mean by category of equivalences? I mean, it's rather. I mean, you can hope that this is given by some kind of kernel in some sense, and then this kernel should be indeed the kind of. There should be some kind of. In order to establish such a thing, you should construct just one category which has simultaneously an action of G of K and G check of K.
Correct. And I'm asking because of one instance of this, I would have expected then in the equivalent in the statement that you're making now, that you're assigning to a particular C, a particular C check, then I would expect that that these two guys have actions of. So the C would have an action of G check, and C check would have an action of G.
Yeah. Oh, yes. Yes. Sorry. There's one thing
because of the previous statement.
No, you're right. I should have put checks here. Thank you. Sorry. Yes. So such things, such D models with this equivalence condition are called Whittaker D models. So it means that the category of Whittaker. So in words, you can say it like this: the category of Whittaker D models on G check is due to the category of representations of the Lie algebra G hat. Now, if you now use this further idea with taking GeO4 invariance, then what we get is that the Kazhdan-Luste category of level kappa, or here, in fact, let me be more careful. Let me write kappa. Let me do what I did before. Write kappa plus kappa critical here. That should be equivalent to the category of D modules of level minus kappa check. Here I can actually, in principle, I should also shift by critical level, but it doesn't. And I mean, yeah, okay. So I didn't say what this thing is, and I don't have time to explain this. This means some twisting of the category of D model. So typical thing you can do is that if you have a say algebraic variety with a line bundle, you can see that algebra of differential operators twisted by this line bundle, and you can also do it if you consider some kind of complex power of this line bundle. Then the complex power itself of a line bundle itself is not defined, but the category of but the algebra of twisted differential operators defined even for complex powers, and this is what you're supposed to do here. And this line bundle is exactly has to do with the corresponding central extension of the group G check of K. So there's some notion of twisted twisted D modules here, which I don't have time to spell out, but so and the point is that here this if I make shift by something integral, then it doesn't change this category of twisted D model. So here I can just leave minus kappa check as it is, and so here I should write G check of minus this U check kappa chi. And here I should write quotient by G of O, G check of O, and quotient G check by G check of O is called the affine Grassmannian. So in fact, if I if I write the affine Grassmannian of G check to be G check of K mod G check of O, then note that here I'm writing quotient on the right, and before it was a quotient on the left. So I can write that this category is the category of Whittaker D modules. So let me write it minus here. Okay, so let me write it now. I'll explain. Whittaker kappa check of the affine Grassmannian of G check. So here by width of something, I mean U check K comma kappa comma chi, sorry, equivariant D modules, and note that here I changed minus kappa check to kappa check, and this actually has to do with the fact that I changed here left quotient by right quotient. So this is what this thing does. So kind of what you get as a byproduct is that this Kazanlusti category, which you can also interpret in terms of quantum groups, should be equivalent to this Whittaker category of level kappa check on the affine Grassmannian of G check. And this is called by Dennis Gabby, this is called FLE, which means fundamental local equivalence, and it was actually conjectured by Lurie and proved by Gatesbury for generic kappa. And by generic, I mean, so in terms, if you think in terms of quantum groups, that kappa means generic. By generic, I mean those values of kappa which correspond to quantum groups outside of roots of unity, and then also by Gatesbury and Lysenko, and independently by Stau-Young for arbitrary, well, essentially arbitrary. So that's kind of state of, now I should say that I'm ignoring some structures here, and namely all these categories are essentially tensor categories. More precisely, what's called factorization categories, and this is actually equivalence of factorization categories. So this is by the way, I should write here of G of, or other maybe of the group G. And this can be also interpreted as, for generic kappa, this can be interpreted as modules over the corresponding quantum group. And so we get some kind of geometric interpretation of the category of modules over the quantum group in this way. Okay, So this is something that has been known for some time, but now I want more examples. And so more examples come from the following, actually come from Lie superalgebras. Now, suppose that I have some suppose I have G, which is now Lie superalgebra. Again, and assume it has an invariant form. Now, I should say that there will be no kind of geometric Langlands for Lie superalgebras. Geometric Langlands will only be for the same kind of usual groups. But the point is that if I have a Lie superalgebra, it means that it's direct sum of even part and odd part. And I'll actually assume, well, in fact, let me assume that I have also the corresponding Lie supergroup. And so, or just it's enough for me to say that this G naught is the Lie algebra of some honest algebraic group G naught, which and this G naught I will assume to be reductive. So again, in a moment will be GLN a product of such elements. Right. So then what you can do is that you can try to play the same game, but you're saying, but you can actually construct, we can look at the category, we can take the category C, which is the category of G hat kappa modules. That category makes sense. So again, it's G hat kappa means that it's the central extension of the corresponding loop Lie super algebra. And the point is that this still has an action of the group G naught of K, of the even part, at level kappa naught, which is just kappa restricted to G naught. So we get more examples of so in this way we get more examples of categories endowed with action of our loop group. And so Gayota, by some kind of, for me, absolutely crazy calculations in string theory, which I'm totally unable to understand, was able to produce, in many examples of this situations, he was able to produce a conjecture saying what the dual category will be. So I want to look at, so today, well, I only have maybe 6 minutes left. So very briefly, I want to talk about just one example. So Gayota essentially started the case of most classical Lie superalgebras. And so as the simplest possible classical Lie superalgebra, the one I want to look at today is the Lie superalgebra G, which is just GLN/M, where N and M are some numbers. Well, I'll normalize them in such a way that I'll always recall N is greater or equal than M. So this has a one-dimensional family, a natural one-dimensional family of invariant forms. So just if you have, so what is GLN-M? It means that you take a superspace of dimension N/M and you consider the corresponding matrices. So here G naught, for example, will be just GLN times GLM, and any kappa will be just kappa the bilinear form kappa computed on A and B. This is just the super trace of well, so some number C, some constant, times the super trace of A times B. That's the one-dimensional family we want to study. So Gallardo produced an answer for this category, which, and in fact, let me note that if m is equal to 0, then we're back to the previous situation. To FLE example. So if we want to sort of produce this kind of answer for arbitrary n and m, then for m equal to 0, we should recover the previous example. Now, unfortunately, I don't have time, so I will only tell you the answer in only one special case. So, but you have to believe me that actually there's an answer in general for m equal to n minus 1. So let me say what it is, and then I'll say what we can actually prove. So, so in this case, the claim is that, so now I'm going to ignore, well, I mean, levels in the sense that, well, you can actually, well, you can actually write down the correct levels and the dual level, but somehow this will just take me too much time to explain the notation. So, so I'll just leave this blank. So, so the claim is that if you can see the category of GLN / m hat kappa modules. Again, I assume that, well, let me now assume that m is indeed is equal to n minus 1. So this is n minus 1. This should be equivalent for some reason to just the category of to the following thing. You don't see any Whittaker, so this should be equivalent to the category of, well, some kind of kappa twisted, some kind of kappa check. I'm going to have to explain what kappa check is, but I won't. Of just D modules, twisted D modules on just the group GLNK. But I now have to explain how my I mean, this is what kind of action does this thing have? This has an action of GLNK times GLMK, which is in this case just GLN minus 1. Okay. Now, how does this thing act here? Well, of course, this has an action of GLN times GLN, but I can choose. There's a kind of natural way to embed GLN minus 1 into GLN. Just consider matrices, kind of block matrices, which look like this. An arbitrary thing here. And this is an embedding of GLN minus 1 of the GLN. So, so here I have on the right, I have a natural action of GLN times GLN, but I only consider the second one, I only view as an action of GLN minus 1. So it gets into this action of GLN K times GLN minus 1 K, where this comes from embedding of this into GLN. So again, this is some conjecture that somehow comes from some calculations on string theory, and I'm absolutely unable to follow these calculations on string theory. But a corollary of this should be that, again, with the right choice of level, if I consider the Kazhdan-Lusztig category for this Lie algebra GLN M of some level kappa, this should be now equivalent. Sorry, this is actually, okay, before I wrote this incorrectly, this should be not equivalent, but this should be dual. If I take the dual, it should be this. And now I take this GO4 invariance, it means I take the Kazhdan-Lusztig category, and this should be equivalent, if you understand, if you follow correctly what's written here, to some kappa check twisted D modules on the affine Grassmannian of GLN, which are here, which are GLN minus 1 all equivariant. That's That's something which you can get as a byproduct. And now this should be some equivalence of categories. And also, at least for generic kappa, this is known to be equivalent to the representations of the quantum, well, let me write it like this, or representations of the quantum G group GLN-M. This, I think, is not known for arbitrary, well, this is known for at least for generic kappa, this thing is known, at least Pavel Leitengov convinced me that this is, that it doesn't really appear in the literature, but it's kind of almost appears in the literature. And so you get so as a byproduct, you get the kind of you get a kind of very particular conjecture. This category of models over the quantum group should be equivalent to this some kind of category of twisted D models on the affine Grassmann of GLN. And in fact, you know, this category of representation of quantum group has a tensor category, and you can also explain, you can also introduce the tensor category, tensor structure on the right-hand side, but I don't have time to do so. So in fact, canonically, it's a factorization category, but we can turn this into tensor structure. So I'm essentially out of time. So let me just finish by saying that what can we prove? What we can prove. So we're trying to prove this equivalence conjecture. We can prove the following. First, we can prove limit version of this, which I don't have time to explain what exactly it says when kappa check is equal to 0. And here we can see the untwisted D modules, and here we can see some degeneration of this category. So it will be actually degeneration will be we'll get representations not of the group GLN-M, but of some degenerate version of the group GLN-M. So that's one thing we can do. And for generic kappa, rather, for generic kappa, we can construct a functor from a tensor functor, in fact, if you introduce the tensor structure correctly, from right-hand side to left-hand side, and about which we can prove the following, such that it is an equivalence for n equal to 2. So for this GL21 case, we can actually prove this Gaussian conjecture. This is surprisingly non-trivial somehow. And B, we know that sends irreducible objects to reducible objects, but we still can't prove that it's an equivalence. And that's a bijection of reducible objects. Okay, I have to stop. So let me just say one last thing, that first of all, there's a version of this for arbitrary n and m, and there's also a version when instead of sort of fine dimensional representations of the quantum group, we consider category O for the quantum group. And then this will actually, then we'll have to, here we'll have to work with some D models, not on the affine Grassmannian of GLN, but on the affine flag variety of GLN. So, essentially everything I said can be done in that case too. All right, I have to stop here, but maybe one last thing I'll say is that there's in principle a version of this for other types of Lie superalgebra. So in fact, this, for instance, this limit version, which is we have a paper where it is proved for the orthosymplectic Lie algebra, but how to put this all in some kind of more general framework, this I don't know, although it is clear that it's very closely related to the forthcoming work of Ben-Zvi, Sakelaridis, and Venkatesh on sort of geometric interpretations of periods of automorphic forms and their connection to L functions. So this is actually, this Gayota conjectures are very, very closely related to that. But I don't have time to explain this. And so again, thank you very much. I have to stop here.
Thank you very much. Other questions? I think Tudor, you can go ahead.
Yeah. Hi, Tudor.
Hey, Sasha. Nice to see you. Quick question. What happens for non-generic K when it's like it's an integer, basically, but not?
Well, okay, I can tell you. You mean like in the general case for this kind of for this whole quantum Langlands story, or in this particular example?
Yeah, well, maybe both. There seem to be multiple options for how these categories change.
Well, okay, so the statement is that if you consider, so the claim is that, well, unfortunately, the actual Langlands, I mean, the kind of geometric Langlands story, I think for generic kappa, it works. It should work just as stated. If you understand the word category in the correct sense, then it should be just a formal mathematical statement. For when you consider kind of zero and infinity level, then it somehow there's some problems. You have to, you have to modify this a little bit, but it's it's related to the story which you might have heard about, but it's nilpotent singular support and so on. But let me say, roughly speaking, what happens. So the claim, so kind of in general case, that if you consider categories with G, well, with just G of K action. So again, G of K action, the notion of G of K action doesn't really change if you shift the level by something integral, but it's kind of convenient to think about level as critical, although any integral level will give you the same thing. Action, that should be the same as categories which in the proper sense leave over the space of de Rham local systems for the dual group. This means local, so means bundles with connections over D star, where D star is the formal function dis. So D star is spec K. Now, again, this is kind of abstract. If you want to turn this into equivalence of categories, so if you have like C and C dual, so they kind of as categories, they can be completely different. But before we took G of O and G check of O invariance on both sides, and we got equivalent categories. So what should you do here? So here on the left, you should still take G of O invariance, and that should be equivalent to the following guide to C check restricted to G check local systems on D rather than rather than D star. So this thing is just note that local systems on the disk. This is just, there's only one local system, but it has, which is trivial, but it has G check worth of automorphism. So this thing is just point mod G check. So this thing is just, so what kind of structure will this have? So this when you restrict C check to this thing, you'll get a category which will have what's called weak action of G check. So it's a category of point over G check, and if you can see here this will have an action of the corresponding Satake category, and it's calling me. Right, and so this is the general story. So for instance, yes, and so you can, well, okay, so this is a general story. Now I can tell you what it amounts to in our kind of super group case. In the case of super group case, it gives you the following equivalence, which is actually proven. Well, again, let me do is m equal to n-1 case, because that's the easiest to say. Otherwise, I'll have to introduce more notation. But the statement is that if you consider, if you consider, I will have this kappa equal to 0 on the left, and then when I consider the corresponding G of O invariance, I will end up with perverse sheaves on the affine Grassmannian of GLN. which are equivariant with respect to GLN minus 1 O. That's note that if I can see that here, just Perosi equivalent with respect to GLN O, I would get geometric Satake would tell me that I would get the category of representations of GLN. But here I can see the equivalence with respect to smaller groups. I get more objects here, and the claim is that this thing is equivalent to modules to representations, finite dimensional representations of the following Gaia. I can see the group, the supergroup GLN M, but also let me denote it by underline. So this is some degenerate version of this. So this is, let me describe an law of Lie algebra. So GLN, this is some degeneration of this group. So in fact, it's an algebraic supergroup, and it's a generation of the following kind. It's well, let me describe an law of Lie algebra or Lie superalgebra. You just take the usual GLMM, but then you set all you set the supercommutator between two odd elements to be 0, and all. So it's so here supercommutator. So or other in this GL and sorry, this M should be in minus 1 here, but you can actually do this. There's a version for the arbitrary M, but so this I can define for arbitrary M. So this in the Lie algebra, supercommutator of two odd elements is 0, and all other supercommutators are as they are in GLMM. So you get this thing, and this thing is actually a theorem. So this appears in our paper. So there's a paper of myself, Finkelberg, Ginsburg, and Travkin. There's actually a better version there for when M is equal to M, which is slightly more complicated, and I don't have time to explain this. But this one is the easiest to describe, and so that's kind of what you get. So in general, you'll get some kind of on the left, you're going to get some kind of category of twisted D models, twisted perverse sheaves, so twisted by the corresponding determinant line, some complex power of some determinant line bundle. And on the right, for generic twisting, you're going to get representations of the corresponding quantum GLN n minus 1 for actual quantum group. But somehow it so happens that here, when you sort of on the right degenerate level to 0, and so here it's sort of the correct degeneration for some reason turns out to be representations of this degenerate version of the, not representation of the corresponding supergroup, but the degenerate version of the supergroup. That's, I don't know if that answers.
Thanks. Yeah, thanks very much.
Any other question? Well, if not, let's thank the speaker again.
Okay, I think we should again I'll thank the organizers since this is the last talk.
Thank you for everyone for coming here, and hopefully we're going to be there in South Africa, and I'm in Poland next year.
Where is it? Sorry, I forgot.
It's
Where
in Poland. So the first one that was online was last year in South Africa, and we were hoping that this year we're gonna be presential, but it wasn't. So next year is in Poland, and hopefully we're gonna be able to make
Poland.
it.
Okay. Well, you know.
Thank you, everyone. Sasha, now that this is officially over, we can close this room. So where's the super part on the left? You have an equivalence there that has some natural Z2 gradient on one side, and I don't see it on the other side.
Well, okay, so this is because I was not very careful. So you actually, you can say it in two different ways. I mean, one way is to actually take this category of, I mean, you can actually sort of keep, first of all, you can just kill the Z2 grade. Namely, so that's one correct formulation. So, well, non-correct formulation, you can actually introduce it on the left-hand side, so by hands, but actually maybe a better way to say it is, I mean, by kill, I mean, it means that you consider this, you know, you have an obvious sort of involution on the category of representation of the supergroup, which is change of parity, and you're just mod out by this thing.
Okay.
That's what I mean by. So I mean, representation of this degenerate supergroup, especially, this is a very well, this GLNM. This is a very clear thing. It's just the following thing. It means that you take exterior algebra, you take Cn plus you take how to say, no, you take, sorry, you take matrices, you take home exterior algebra of the following space, home Cn to Cm times home in the opposite direction. Take exterior algebra here, take take modules over this exterior algebra without any grading, and then you take modules. Well, maybe let me write it like this. I want to take sort of, well, this algebra has an action of the group GLM cross GLM. All right, let's call this algebra A, for instance, and then I take then your categories, you take category of.
So that's the algebra of functions on the odd part of the Lie algebra, and you're acting by the even part of the group, right? So
no, it's not no, it's not functions, rather universal developing algebra, because I killed all odd supercommutator.
You killed the commutator. So yeah, that's
yeah. So so then I consider just GLM times GLM.
Okay.
Equivariant modules over A.
Okay, so this is third. Okay.
This is what I mean by modules over this. And of course, you can actually say that this algebra is actually Z2 graded, and you can consider Z2 graded modules. But for the purposes of this, I'm actually killing the Z2 grade.
And coming back to my first question, so would you expect this equivalence of two categories to be some sort of push-pull diagram?
Certainly, no. I mean, it's again. So and that means that, and that's what Dennis actually likes to say, that for this, it's just enough to construct just one category endowed with an action of, you know,
both sides, yeah,
of both sides. So so this should be kind of universal Langlands category, which has action of G of K on some level and G check of K on the dual level.
Right.
So if you constructed that, then somehow, and you know, and there are some conjectures about how to construct it, but somehow it's all kind of conjectural. And
I see. Okay. All right. Thank you very much.
So in fact, I can say, so if you can also work and do it in both in the other direction. So if you believe that such equivalence exists, then the way to construct this category is the following. You take the category of D modules on G of K on the corresponding level, and then it has two actions of G of K on the left and on the right. And we apply this Langlands duality with respect to this right action, for example.
No, I'm sorry, I missed. So
I'm saying that let's consider the category of D modules, let's say some D kappa modules on G of K. This has two G of K actions.
Yes.
by left and right translations. And then apply this Langlands duality with respect to say right action. Then kind of by definition you'll get a category which is now as so it's so I'm saying that
that doesn't give you that doesn't tell you what the
no, it doesn't give you
is.
construction, but I'm just saying that if you believe that such a functor exists, that the way to construct this universal category is this: just apply this functor to this category with respect to one of the actions.
Yeah. Okay, so before I leave, I'll ask you a favor. Could you, by any chance, email me the PDF of this so that I can?
Yeah, I mean, maybe I'll edit it a little bit and then I'll send it to you maybe tomorrow.
Thank you very much.
Okay.
All right. Thank you, Saja.
Okay.
Bye-bye.